So now you should be able to see my screen. So thank you for the kind introduction. And dear Prize Committee, dear ladies and gentlemen, it's my great pleasure and a great honor to speak to you today about my work on numerical homogenization for nonlinear, strongly monotone problems, a work which recently appeared online in the in IMA Journal of Numerical Analysis. Let me start by motivating this piece of research. As you probably know, linear material laws like Hooke's law or Darcy's law are only valid in certain regimes. And if we go, for instance, to higher intensities or higher stresses and forces, we need to account for this by taking nonlinear material laws. This occurs, for instance, in non-Newtonian fluids or also in stationary Richards equation. In this talk, we will look at the following prototypical nonlinear equation minus divergence of A equals F, where A depends on the spatial variable X and the gradient of the sought solution U. Further details and assumptions on A and F will be given later on. But let me already highlight here that the shift from the linear to the nonlinear world comes with a couple of new challenges in numerical analysis. Two examples to illustrate this are, for instance, that optimal order L2 estimates were only discovered and proven by Abdul and Weimar in 2012 because the traditional Obinice trick, you know, from the linear world is no longer directly applicable. A similar situation occurs, although being discovered slightly earlier, but still late in comparison to the linear counterpart, is the effect of numerical integration. So the first challenge we identified for this work is our nonlinear PDEs. What is also equally important when considering practical applications is the inclusion of multi-scale features. You see a prototypical picture of the spatial dependence of A on the right-hand side. This may occur, for instance, in groundwater flow, where the flow itself goes over several meters or hundreds of meters, while the soil material changes on smaller, very small scales of centimeters. So we have fine spatial multiscale features in our coefficient A here. And as you probably all know, standard discretization techniques like the finite element method now require to resolve all these scales in A in order to obtain a good approximation. This, however, comes with a huge and in many situations impractical computational effort. We will discuss this problem a bit more in detail later on again. But summarizing the present work, details with the combined challenge of nonlinear and multiscale problems. Of course, and there is already some existing work in that direction that I want to briefly summarize. It starts back with the seminal work of Allard in 1992, where analytical homogenization results also for nonlinear problems were obtained. Basically, they say something like in the limit of vanishing fine scale properties, you have a certain, the solutions converge to a certain limit solution and limit problem. Based upon these analytical results, numerical methods were designed. First and foremost, the finite element heterogeneous multiscale method, developed by Asya Abdul and co-workers in a series of papers, and also Patrick Henning and Mario Ulberger. In a similar spirit, I should also mention the sparse multiscale finite element method by Huang, and the multiscale finite element method and the generalized multiscale finite element developed in various papers by Ifeniev and co-workers and Chung and co-workers. All these methods have in common that they build up a multi-scale basis by solving locally some fine-scale problems, which are also of nonlinear type. at least in the numerical analysis, in many cases, these methods are restricted to certain assumptions on the multiscale features of A, such as local periodicity, or at least some scale separation, meaning that you have a clear separation between the length scale of your computational domain and the scale on which A is spatially varying. To overcome these limitations of local periodicity and scale separation, for instance, the localized orthogonal decomposition method was designed. So far, it has been only studied in the linear and semi-linear world, with the two notable semi-linear contributions in two papers by Henning and co-workers on semi-linear equations themselves and the Gross-Pitayevsky eigenvalue problem, which is also of semi-linear nature. In this literature review, I should also mention the very recent preprint by Liu and co-workers on generalized rough polyharmonic splines that somewhat falls into a related spirit to what I will present you in the following. Let me already highlight the main contributions you will see throughout this talk. As already mentioned, the aim is to design and analyze a multiscale method in the spirit of the localized orthogonal decomposition. The main feature of this method is that we again construct a multiscale basis, but in this case, these basis functions are the solution of linear problems and not nonlinear problems. I will show to you a priori error estimates and discuss choices and procedures for the linearization that is necessary to build up these linear problems for the multiscale basis. With that, let me give you an overview of today's talk. You've already seen the introduction into the problem. Next, I will give you a thorough problem formulation and discuss the finite element discretization for it, where I also introduce some necessary notation. The main part of this talk concerns the computational multiscale method, which I will try to present at length, and the error analysis. I will close with some illustrating numerical examples. So as promised, let me show to you the model problem we're going to look at in this talk. I directly write it in its variational form. So we seek the weak solution U in H10 of the following nonlinear problem, where the left-hand side is abbreviated by this form curly V. As source term, we have a volume term F, which we assume to be an L2. The nonlinearity A depends on the spatial variable and the gradient of the solution, and we make the following assumptions. With respect to the spatial variable, A is assumed to be an L infinity only, so that especially we allow jumps and discontinuities. With respect to the nonlinearity, we assume a bit more higher regularity, namely C1, so that in particular, you can build the first derivative with respect to the second variable of A. Moreover, with respect to the second variable, we assume a Lipschitz condition on A and the so-called strict monotonicity condition. They can be imagined to replace the boundedness and uniform ellipticity assumption that you have in linear problems. And finally, we make the technical assumption that if we insert 0 into our nonlinearity, we can bound A by an x-dependent constant. You should always keep in mind that although I do not write a fine scale parameter here explicitly, we implicitly assume that there is a multi-scale nature in the spatial variable. So having this nonlinear monotone model problem at mind, let me discuss the finite element discretizations. By TH, I denote a shape regular simplicial mesh of omega, where omega in this setting is assumed to be polyhedral so that the mesh is exactly fitting. TH is denoted as a coarse mesh in the sense that the mesh size H does not necessarily resolve the variations in A. Built upon this mesh, I denote by VH the lowest order Lagrange finite element space, so the subspace of H10, which consists of piecewise affine functions. The standard finite element method now seeks in a Galerkin method the solution UH, the discrete solution UH in this finite element space VH, solution of the following nonlinear discrete problem. This nonlinear system resulting of this problem can be solved with a method of your choice, for instance, Newton's method. Classical a priori estimates for the standard finite element method, summarized, for instance, in this work, but going back to earlier works of other authors as well, show to you that the error between the exact solution U and the discrete solution UH in the H1 norm is of the order H, so linear convergence, and in the L2 norm, we have quadratic convergence. Two things need to be noted about these estimates, though. First of all, in order to have them, you need to assume that the exact solution U is an H2, a regularity which is not necessarily satisfied in case that A has spatial discontinuities, for example. Secondly, what is a bit more hidden, in this constant C here, there stand also spatial variations of our coefficient A. And if A is rapidly oscillating on a small scale, this constant can be very large, and in particular, these estimates are only valuable in the so-called asymptotic regime, namely where your mesh size is resolving the variations of your coefficient A. So this is why we do not want to consider a standard finite element method because of its high computational complexity for the situations we are interested in. Instead, we will now look at the design and design of a computational multiscale method. Let me start with a bit more notation. We assume that we have at hand a bounded and local linear projection operator IH mapping from H10 into the finite element space. So this is a projection type operator with standard with H1 stability and standard L2 approximation properties. One example that you can keep in mind, if you like, is that on each element you do an L2 projection, and then afterwards you do some Oswald type averaging at each vertex of your mesh in order to obtain a continuous function. Because of its stability and surjectivity, IH induces a splitting of the solution space H10 into the finite element space and the kernel space W. So this kernel space W we can see as the space of functions with fine scale oscillations, so oscillations that are not seen on the scale capital H, and especially not by the finite element space. And the goal of this method is now to replace this finite element space VH by an equally dimensional multi-scale space that has better approximation properties in a Galerkin procedure than the finite element space itself. In order to do so, we will first look at what happens if we write down the methodology that is available in the linear elliptic case, developed, for instance, especially by Axel Morquist and Daniel Petersheim, if we write this down also for our nonlinear problem. And this is also to recall to you, to those of you who've maybe not seen this method so far, how it works. It's a Galerkin method, so we seek our discrete solution in a special multiscale space I will comment on later, that we use as test and ansatz space for our nonlinear discrete problem. This special multiscale space is constructed in such a way that it is orthogonal to all the functions in the kernel space and orthogonal with respect to the problem form curly B. In other words, you can express this multiscale space as the finite element space minus some so-called corrections, where this correction operator Q maps from the finite element space into this kernel space and exactly realizes this orthogonal projection. this is how it works for the linear case, and we can write it down as well for the nonlinear case. But then we should note that B is nonlinear with respect to its first argument, so that this operator Q is a nonlinear operator. This in turn means that this multi-scale space in the method is a nonlinear space. So especially it's not a linear vector space. This comes with a couple of challenges. First of all, this nonlinear space setting makes it necessary to really deeply consider whether this is all well defined. Secondly, even if everything is well defined, and we have a rather complicated coupling between this problem on top that we really want to solve and these kind of auxiliary problems we need to solve in order to build up the multi-scale basis. And this is the motivation why we try to simplify this method, and we will do this in the construction of these correction operators. So this is how we come to the linearized multiscale method. It's still a Galerkin method where we seek the multiscale solution in a multiscale space, solution of the nonlinear discrete problem. But now this multiscale space is really a linear space. It's still constructed as the finite element space minus some correction operators. The correction operators still mapping from the finite element space to the kernel space, but now they are defined via linear problems. Namely, these correction operators realize an orthogonal projection with respect to this curly A, which is a bilinear form with a uniformly elliptic matrix fractal A. So this is what I mean by that we are solving linearized elliptic corrector problems here. So in this writing, this curly A here is completely arbitrary. But when choosing this curly A, we need to be careful because the good approximation properties of our multiscale space are intimately linked to the fact that ideally we would like A to be the form B, the nonlinear form B, which is of course impossible as or not desirable as we discussed before. But still we need to have a certain link between B and A in order to obtain the good approximation properties. So let me discuss in more detail how we can choose A. So I've repeated the linearized corrector problems here for you to remember them. And the choice of curly A or fractal A is now done via linearization. So you replace your nonlinear function A of x and gradient v by a linearized model AL that depends on the spatial variable x, the choice of your linearization point, gradient of u star, and gradient of v, and it's affine with respect to this last argument so that you can write it in the following form. And then as fractal A, you pick this boldface AL, evaluated at your fixed linearization point u star. So at this point, we have replaced the question of how to choose fractal A by the question on how to choose the linearization model and how to choose the linearization point. We will discuss the choice of the linearization point later on, but let me give you here two typical choices for this linearization model. The first one is a Newton type linearization where you choose fractal A as the Jacobian of A with respect to the second variable evaluated at your linearization point. The second choice is a so-called Kachanov type choice, which works for nonlinearities of this form and then freezes the nonlinearity here at your linearization point u star. Let me emphasize that in the perfectly linear setting, both choices lead to the same method, namely the method that is known in the linear case, where this curly A equals the bilinear form B. Moreover, let me emphasize that these two models for linearization are inspired by typical nonlinear iteration schemes, but you don't need to choose the same iteration scheme for solving your discrete problem as you chose for your linearization and your choice of fractal A. This is completely independent. So for example, you could choose to solve your nonlinear discrete problem by Newton's method, but still obtain your fractal A through a Kachanov type linearization. So we've discussed the linearization of our methodology, so how to construct linearized corrector problems queue. Still, this queue is not directly usable because it's defined via the solution of a problem which is posed on the whole computational domain and seeks a solution and has test functions in the space W of functions with fine scale oscillations. So in the end, this means that in order to compute Q, we have to solve global fine scale problems, which is very costly and needs to be avoided. What helps us out, however, is that we are in a linear setting when considering Q, which has been well studied in these works by Patrick Henning and Axel Morquist and Patrick Henning and Daniel Petersheim, and where we have the result that the correction operator Q is exponentially decaying. More precisely, for example, if you apply this correction operator Q to a head function lambda z, which has a very local support, Q of lambda z will have a global support, but the absolute values of Q of lambda z will be very small. This is illustrated in the picture below here. So we look at the head function centered here, and the color coding shows you a logarithmic color coding of the absolute value of Q of lambda z. And you see if we are outside this region here, for instance, we have values of 10 to the minus 4 or lower. So we can more or less safely hope that if we discard all these contributions here, that still this gives a good approximation of this ideal correction operator. And this is exactly what we do in the localization step, namely that we truncate the computation of our correctors to local subdomains. Let me formalize this. So first of all, in order for quadrilateral mesh, let me sketch this. So if we have an element T here, we first introduce a so-called patch around T. So for example, the patches of all the elements around T, and then the second layer patch yet another layer of elements around T, and so on. And so we try to truncate everything to these patches. And in order to do so, we introduce these localized spaces, W of nm of T, which are the kernel space, but now restricted to functions in this patch and extended by 0 outside. And then we can define localized corrector problems where we seek solutions Q, T, M, J. T is the element, M is this so-called oversampling parameter indicating how many layers of elements I take in my patch domain, and J is the coordinate direction here. So QTMJ is kind of the correction operator for the coordinate direction xj. And then on these patches just explained, we solve the following projection elliptic problem with this fractal A here. For those of you into homogenization theory, this writing may remind you of classical cell problem. So I've defined this QTMJ, and they can be used also to define a truncated correction operator QM. I don't want to write it down in full technical details, but you should recall that QM can be constructed, and it can be seen as a localization or truncation and replacement of this ideal operator Q that would have global support as discussed before. So with that, we can define our localized method. So I've written down the localized corrector problems from the previous slide once more, and they are used to define your localized multiscale space VHM. You can define it as, again, as the final element space minus now these truncated correction operators QM. So beforehand, there was only a Q. Now we replace it by QM. And we can explicitly also give a basis for this space. Namely, it consists of the following basis functions. We take the hat functions, these lambda z we know from finite element theory, and subtract QM of lambda z, which can be written in the following form. You sum over all the elements that have z as a vertex. You sum over all space dimensions, take the j spatial derivative of lambda z, and multiply it with these localized corrector functions I've just defined here above. No matter how exactly this localized multiscale space looks like, the message is here that we have an explicit basis for it that we can compute. And therefore, we can also compute our localized multiscale solution, UHM, in this new space as, again, a Galerkin solution of the following nonlinear problem here. And this nonlinear discrete problem, again, can be solved with the method of your choice. Having seen and developed this numerical method, let me now give you a glimpse of its error analysis. The main theorem in this work is the following a priori error estimate. It bounds the error between the exact solution and the multiscale solution UHM in the H1 semi-norm. And it says that it's of the order H, so the match size, plus some term which is exponentially decaying in this oversampling parameter, so how many layers you take in your local patch domain, times the right-hand side, plus some linearization error I will comment on in a minute. Let me highlight that this first part here is exactly what we expect from the linear theory already. In particular, it tells you that if you choose m to be like the logarithm of h, that then this your energy error is decaying linearly or converging linearly. And there are two more things to highlight here. First of all, we don't need more than u in H1 in order to hold for this estimate in order to hold, so no higher regularity required. And second, in this tilde notation here, there are no spatial derivatives of A hidden. There are only kind of the spectral bounds of A hidden, so the Lipschitz continuity constant and the strict monotonicity constant. And as mentioned, all this holds up to a so-called linearization error that is written down here. And you see that the essential part is the difference between the nonlinearity and its linearization model at the linearization point u star. And for the two linearization models we've discussed so far, you can give some easy bounds on this linearization error. Basically, these linearization errors tell you that that you have to bound the error between u, the exact solution, and your linearization point u star in the H1 norm. And for the Newton type linearization, you have an additionally W1 infinity error here. In the paper itself, there are other variants of this a priori error estimate given as well that are basically of a similar form, but with a different linearization error that, for instance, in one version allows you to have these linearization errors split into kind of local contributions. But in the end, the theorem and the estimate on the linearization error tells you that u star, your linearization point, should be close to the exact solution u. So ideally, you would insert u as your linearization point, but of course you cannot do this because the exact solution is not known. But having this in mind, let me discuss possible choices of u star here with you. The first thing, kind of a no-brainer, is that you have to pick a function u0 anyway to start your nonlinear iteration for your global problem later on anyhow. And you can choose this as your linearization point. The next kind of level would be to compute the coarse finite element solution UH, which is also very low cost, low in computational cost, and use this as your linearization error. Note that we said that UH is not a good approximation to U, but nevertheless, you can think that it already may include certain information on your problem and is maybe better than a simple guess of your linearization point. The highest, and somewhat highest level of things you could think of is to what I call a cascade of Lod solutions, meaning that you start with a guessing of your linearization point, compute your Lod solution, and use that then again as a new linearization point, computing yet another Lod solution. In this cascade, you can think also of adaptive strategies. So if you update your linearization point, considering how much of your multi-scale basis and where you have to adapt it at how. And moreover, you can think of this cascade also to be done directly within the nonlinear iteration, so that you don't solve to a given accuracy with a certain linearization point, but that after certain steps of your linearization, you reevaluate and take a new linearization point together with adaptive strategies on how to recompute the multi-scale basis and where. And such an adaptive iterative scheme I consider together with my colleague Roland Meyer from Gothenburg for the nonlinear Helmholtz equation. So after this work, and in a similar spirit, some adaptive and iterative strategies are also discussed for the generalized rough polyharmonic splines in this very recent preprint by Liu and co-workers. So with a view to time, let me come to some illustrative numerical experiments. In the first experiment, we have the following nonlinearity. And the spatial dependence of A is of a periodic type with a periodicity length of 2 to the minus 5. And you see the spatial pattern of A on the bottom left. We choose a source of a Gaussian type, which is scaled in its amplitude in such a way that the solution U, which is depicted here on the right, has a maximal value of around 1, so that you really have some gradients in there that can that influence your nonlinearity. Let us first have a look at the convergence of the error, the relative error in the H1 norm, so what we bounded in our theory. And we see here in the curves that for already small layer parameters m equal 2 or 3, we obtain this linear convergence here, and in particular are performing much better than the finite element method, which is up here, and which is stagnating in this pre-asymptotic regime here. So at this point, we exactly resolve the periodicity pattern of A. And let us, so all these results were obtained with the linearization point U star equal to 0. And now let's compare different choices of linearization points. So the blue curve here on the right is the linearization at 0, so exactly what you saw on the left. In green and black, you see two linearization points chosen in the finite element space, especially this black line is the linearization at the coarse finite element solution. As you see, in this example, it does not give you an advantage over a simple linearization at 0. What is notable, however, is the red curve here, which is kind of the first cascade of Lod solutions. So meaning that we took the solution of the blue line as a linearization point in order to compute yet another multi-scale solution. And you really see that this improves your errors, still gives you a linear convergence with a small slowdown of the convergence here in the regime where you're about to resolve the periodicity, but which is typical. In the second example, I want to move on from a very structured coefficient to a really unstructured coefficient, namely the spatial dependency here is of a kind of random type in the sense that we choose it to be piecewise constant on a scale 2 to the -6 with random values in 0.11 drawn for each small square. We have the following nonlinearity that does not fulfill all of the assumptions laid out at the very beginning. And we choose a source F, which is an L2 only, so no hierarchy. We consider for this example a Petrov-Galerkin formulation, so where only the test functions are the modified multiscale functions, but the solution and the ansatz and functions and the solution lie in the standard finite element space. With that, you cannot hope for a convergence in the energy in the H1 norm, but you can hope and prove that the solution, that the error between the exact solution and your Petrov-Galerkin approximation in the L2 norm is converging as the L2 best approximation in the finite element space, which is depicted in this dashed line with the triangles. And you really see that we follow this with our method up to some stagnation here at the very end, which is possibly due to a dominating linearization error. And in particular, let me stress that the finite element solution lies in the same space. So this finite element solution lies in the same space as the multiscale solution in this case, and we are able to almost find the best approximation, which is not found by the finite element solution. Finally, let me show you an example for stationary Richards equation, where we have a quasi-linear non-monotone coefficient, which depends non-linearly on the solution and not the gradient. The spatial parameter C here is shown on the left picture and especially includes a high contrast channel. The nonlinearity is the so-called van Genuchten model, which is quite popular in considering stationary Richards equation. And although this model does not fall into the class we analyzed in the paper, you still see the linear convergence of the method as expected. With that, it's, I think, already time to wrap up. So as a summary, I've presented to you a multi-scale method for nonlinear problems beyond the assumptions of periodicity and scale separation. The important feature is that we generated a problem-adapted basis in a linearized and localized fashion. I've shown you optimal error estimates with respect to the mesh size up to a linearization error. And in that spirit, we compared analytically and numerically different linearization strategies. Concluding, let me say that I think that this paper and also the ensuing adaptive iterative multi-scale methods open up a new gate and new perspective on nonlinear multi-scale problems, and especially adaptive iterative multi-scale methods are quite promising and should be studied in the future also for quasi-linear problems. And beyond that, of course, the application to other nonlinear problems and problem classes is of high interest and may be considered in the future. And with that, I would like to thank you for your attention, and I'm open to your questions.
Okay, thank you, Barbara. That's a very good talk. So as I mentioned earlier, please feel free to type questions into the Q&A, or if you're a panelist, tell me on the chat. Let me begin, Barbara, asking, do you have any feel for how sharp the error bounds that you've derived are?
Yeah, it's really a question of the linearization error, and I must admit that the estimates for the linearization error I showed to you are rather rough and simple estimates here. but in general, with respect to the order in the mesh size, this is sharp if you do not assume any higher regularity. If you have higher regularity of your right-hand side, of course, you will also observe some higher order convergence rates. So it's sharp in the sense that you should think of the convergence rates and not the exact constants involved there.
Yep, sure. Okay, thank you. And I think Alex has a question.
Hi, Barbara. Thank you for a nice talk. So because your bounds now have implicit constants that only depend on spectral properties of A, does that mean you have a better understanding of the pollution effect that you might get for, let's say, a Helmholtz-like problem?
Oh yeah, Helmholtz-like problems are yet another story. So in this tilde notation, I don't know whether I got your question right. The spectral bounds of A, they are hidden in this tilde notation. So, but what is important is that you don't have spatial derivatives of A in there. Right. And yeah, these works we also did some works, or other authors have done something for linear Helmholtz, and have done something for nonlinear Helmholtz, where in some sense you can to a certain extent reduce the pollution effect in the sense that the mesh has only to resolve your wavelength, but your this parameter m has to slightly grow with the wave number, namely logarithmically. It's in some sense like the polynomial order has to grow logarithmically in HP elements. So it's of the same quality, the estimate, of the same spirit, although these methods are possibly not related at all, but just to keep it in mind.
And you made a comment on this slide about it's good to, or there's advantage of using a linearization so that U minus U star can be thought of as partitioned onto each element, which you don't get for these Newton type methods. What was the advantage that you were thinking of here when you said?
Yeah, so I have a variant of this linearization error, which basically splits this up into local contributions. And this is especially interesting, not in these a priori estimates, but if you go to adaptive strategies, then you can really say, okay, I only have to recompute the correction operators on those elements where this linearization error is large. And for the others, I don't have to do anything.
Got you, thanks, yeah.
Okay, thanks, Alex. Oh, there's a Q&A, I think, popped up. Here's a question from Andre Souli. Thanks for the nice talk. Have you thought about P. Laplace type homogenization problems where you would be outside the Hilbert space setting of H1? The nonlinearity would still be monotone in that case, but not uniformly Lipschitz. I think you can read that yourself, Barbara, if you go into Q&A.
Yeah, I saw this question. Thank you very much. Sorry, I have a fly here which wants to say something about the talk, apparently. Yeah, I've thought about P. Laplace type problems, but not dug into it so far. So I think this not uniformly Lipschitz would need to be considered. And yeah, it really depends on P. Laplace. I think this is a demanding problem because the nonlinearities can really be strong in that case, but it's certainly of an interesting application for the future.
Okay, thank you. And then maybe finally, Barbara, this was touched on in Alex's question, but you mentioned the Kachanov versus Newton. Which of those is better under which circumstances in your context, do you think?
Yeah, this is a really interesting question. Thank you. I must admit that I have not compared them in very much detail. I just mention them as typical examples because they are also quite commonly used in different things. So personally, I always solved with Newton's method and also chose this Newton type linearization. But I think for the examples here, I considered you could also do the Kachanov type linearization if your model has the proper form. And of course, with these iteration schemes, you have different assumptions on in order to when these types of iterations converge. I'm not too much into the into their exact form, to be honest.
Yep, okay, that's fine. Thank you. That's a good answer. I don't see any further questions, and we're coming up to the next speaker's slot, so I think we'll finish there. So thank you, Barbara, for that presentation.
Yeah, thank you, Ash.